10.
But why some
9,
say the moon?
Ignition sequence
Why
start.
choose this as our
6,
goal?
5.
We choose
4,
to go to the
3,
moon in this decade
2,
and do the other
1.
things. Not
0.
because they
All
are
engine
easy,
running.
but because they are hard.
Liftoff. We have a liftoff. 32 minutes past the hour.
Greetings and salutations. Welcome back to Everything Astronomy. I'm Joe, and today I'm joined by Michael and Tommy. Unfortunately, Sam couldn't be with us, but rest assured he will be next week. Today, we were planning on talking about dark matter, and dark matter is obviously a fairly mysterious subject matter. And so to talk about dark matter, we're going to cover three big areas. First of all, the history of the science of dark matter. So who first thought of it, how it was conceptualized, the different theories that used to exist about what this dark matter could be. Then we're going to talk about the different methods of actually observing dark matter and the evidence that we have for dark matter's existence. And then lastly, we're going to talk about what dark matter could actually be. So if it's a particle or not, and then lastly, we're going to talk about alternatives to dark matter. If dark matter doesn't exist, then what exactly would that look like?
Before we get into it, we also wanted to add a new segment to Not So Sirius, where we cover some very recent scientific news that we find that we think might be interesting to our audience. And so at the beginning of every Not So Sirius episode from here on out, we want to just briefly cover some scientific news, explaining what these articles mean, just to pique some interest in different topics that are happening that don't necessarily have to do with astronomy.
And if you'd like to read the articles we are referencing in the news segment, they are linked below in the description, or you can find them on our website.
Welcome to our first news segment. The first article that I want to cover is physicists have been able to braid a two-dimensional particle called an anion. Essentially, an anion is a class of particles. There's three classes of particles: a fermion and a boson, as well as an anion. Electrons, for example, are fermions, whereas photons or particles of light are bosons. Anions are a third class of particle, but they're strictly two-dimensional. And so we won't be able to detect them very well in the 3D universe that we live in, but physicists have just recently been able to braid together anions, essentially like a rope, in the two-dimensional plane that they live in, altering their quantum states and leading to very interesting effects that they are continuing to pursue.
Another news story this past week related to the topic, dark matter, is the search for a particle known as an axion. And so particle physicists recently have been using mines underground, whether that be in the US or in other countries around the world. And so this experiment is based a few thousand feet underneath a mountain in Italy known as Gran Sasso, and they found an abnormal background noise that's unexplained. It could be due, they think, possibly to trace amounts of a radioactive material, but they're not sure. And so they have an experiment that's coming up later this year to hopefully confirm that it's either what's known as a solar axion, or just the background noise from that known radioactive isotope. And so this experiment uses something known as xenon. It's a noble element, so it's inert, and so it's very useful in these experiments. And the one thing that's different for an axion is that when they look for these signals of these particles passing through these giant, I think it's 3.2 tons of liquid xenon, when they look for these particles passing through these vats, usually they look for a signal coming from when it strikes the nucleus of the xenon atom. But in this example, the axion wouldn't hit the nucleus, instead it would hit the electron. And so they look for an electric kind of signal to kind of measure how many axions are passing through. But as I mentioned, they're not too sure, and they're going to have follow-up experiments later this year.
We know that there is something out there that our current physics and understanding of the world cannot explain. And that something is that when we look at how galaxies behave and how the universe behaves on the large scale, there appears to be a lot more mass than we can account for through stars and dust and regular matter. And so since the 1930s, this has led scientists to coin this quote unquote missing mass dark matter. And it seems that dark matter weighs that there is 5 times more dark matter than there is regular matter in the universe. And one of the big uncertainties, and something that scientists have been trying to solve for the last 90 years now, is determining what this dark or missing matter is. Because even though we know that there is something out there, we don't know what that something is. And so this has been kind of blowing scientists' mind since the 1930s, when the idea was first introduced by a man called Fritz Zwicky.
Yep. And so Fritz Zwicky in the 1930s, 1933, I believe it was, he's a Swedish astronomer working in America, and he studied galaxies and galaxy evolution. So basically how galaxies change over time and interact with each other. And he observed a group of galaxies. These galaxy clusters can range from a few galaxies near each other to nearly 100 galaxies in the general area, with a common center of mass they share. And he observed that these galaxies were moving too fast than theoretically they should be. And so there was some type of missing mass. And so he came up with an estimate that the galaxy cluster, I think it was called the Cosima galaxy cluster, had 400 times the mass it should have had based off of Newtonian mechanics or Newtonian physics.
Mm-hmm. And that was kind of based off of the gravitational lensing from the light behind it, and just the behavior of all the galaxies that were within the Cosima galaxy cluster. But then moving on to the 1950s, there's a grad student at Cornell called Vera Rubin, who actually, there's a field of astronomy where you look at the rotational physics of a specific galaxy. So as many of you may know, the Milky Way is a spiral galaxy. And so with the spirals, you're able to take a lot of data. And one of the types of data they take are looking at the rotational curves of a galaxy, essentially how fast different points from the center of the galaxy are moving in correlation to one another. And so in 1950, when Vera Rubin was looking at individual rotation curves of galaxies, he noticed that far beyond the matter that we could see, all the stars, far beyond the outside of the galaxy, the speed of the galaxy hadn't slowed down, suggesting there was lots and lots of matter that was essentially invisible that was causing the outside of the galaxy to rotate very quickly.
Yeah.
And so I think the best analogy for this is not looking at the data from Fritz Zwicky, where he looked at galaxy clusters, because it can be a bit confusing looking at the outward and forward velocities of those galaxies. But it's best to think of first the solar system and what Newtonian physics would predict. And so we have the sun at the center of our solar system, the first planet being Mercury, and we expect Mercury to go quite quickly in orbit around the sun. And then, of course, the further you move out, the slower the planet goes around the sun. So whether you think we have a ninth planet known as Pluto, or whether you know it's Neptune, that planet is obviously moving slower than Mercury is right next to it.
And that's just to stay in kind of the circular orbit that it's going around. So in order for things to stay going in a circular pattern around the central object, or in the solar system's case, the sun, they have, the further out they are, so the bigger the circle they make, the slower they have to be going.
Mm-hmm.
Right.
And so when astronomers first looked at galaxies, there was no reason to suspect that would be any different. It should just be a larger version physically of a solar system that we observed before, except it wasn't. And so the best way is to look at what Vera Rubin saw, and look at the simplest way is to look at the galaxy rotational curve. So how far out are we moving at this, about 2/3 of the way out from the center of our Milky Way galaxy versus the stars on the very, very far ends of the Milky Way galaxy. And if we thought of it in terms of the solar system model, we should be moving a little bit faster than the stars on the far out the far reaches of our Milky Way galaxy, except
Mhm.
we're not. And so Vera Rubin in the 1950, as Tom mentioned, looked at distant galaxies and measured the rotational curves. And instead of seeing the velocity drop off as you increase distance from the center of the galaxy, she saw that the rotational curve, it's called, kind of flattened off. And we call this a flat rotational curve.
Right.
And so the velocities did not decrease the further you went out. And the only way to explain this was that there seemed to be some unaccounted for mass that was kind of holding those objects on the outside of the galaxy close in at moving at high velocities or higher velocities than expected.
Mhm.
Yeah. So at that point, all we know is that that what we're seeing doesn't match the predictions made by classical mechanics, and
Right.
we're thinking, this is weird. There seems, to explain this phenomenon, there must be a lot more mass than we can see and account for.
Mhm.
And so if you Princeton physicists, one named Ostreicher and the other one Jim Peebles in 1973, they ran a simulation of the Milky Way galaxy, our home galaxy, on their computers, and they included one simulation without dark matter and one without dark matter. And so without dark matter, at the velocities that we observe at the outside of our own galaxy and other galaxies, all those stars should fly apart without the presence of dark matter. But once you put dark matter in those simulations, you see that extra mass, even though we can't observe it, and we still to this day don't understand what exactly that mass is or where it comes from, it still kind of gravitationally holds those outer stars at the outside of galaxies to our galaxy, so they don't fly away at those high velocities that we observe them to be moving.
Right.
Yeah.
Yeah, and Vera Rubin continued to make progress on rotational curves, as well as an instrument maker named Kent Ford, well into the late 1970s. And so even as of 1980, there's already a threefold case for the presence of this missing mass that we now call dark matter, where Franz Zwicky in 1933 noticed gravitational lensing from a mass 400 times greater than he should have seen in that Cosima galaxy cluster, as well as the galaxy rotational curves that Vera Rubin had found in 1950 that were then backed up by simulations 23 years later in 1973.
And I should mention, I'm not sure if Fritz Zwicky used gravitational lensing to first find it. I think it was just the velocities of those galaxies,
I think it
and not
was.
lensing. I don't
think
think the instrumentation was refined enough to be able to observe those small glitches or the small lensing. Also, it's good to also mention that Fritz Zwicky was a little bit abnormal, at least in the astronomy community. A lot of people, not only with dark matter, but a lot of people thought he was a kind of crazy for this idea of dark matter. And it really wasn't. There's 15 years between when he first proposed it in a paper and when Vera Rubin and other astronomers picked up the idea and actually saw it as being legitimate. So there was a while there where it wasn't really that much of a talk in the astronomy community.
Yeah, he was known for his rather eccentric and unconventional approaches and problems. And so another thing is that, even though physicists and astronomers were observing that there should be more mass, no one exactly knew how to explain what this mass was, because we were seeing, the solution to fixing what Newton was predicting was to add more mass. But obviously that entails two possibilities. Either A, Newton is wrong, and so then we need to revise the way that we're thinking about gravity at galactic or larger scales. So that's the first possibility. Or the second possibility is that there exists another kind of matter that doesn't seem to interact with light, but that exerts gravitational force and that interacts gravitationally. And so you have these two possibilities that are kind of, they go against one another, that either dark matter is a physical thing, it's a particle, it's palpable probably in some way, or you have this thing that Newton's laws are wrong, and so we're not actually looking at missing mass, we're just looking at incorrect mathematical predictions. And nearly, I believe, since the beginning of our search for this quote-unquote missing mass or dark matter, the idea that Newton is wrong has been more or less ruled out.
Right.
But we'll cover those approaches. But so essentially for the last, I don't know, since I think the 80s, scientists have been looking for the matter version of dark matter and have been trying to detect the dark matter particle. And there's been lots and lots of attempts since looking at different versions of the dark matter particle. So it could be huge, it could be very little, it could exist in all sorts of different forms. And I mean, it started out, I believe, in 1987 in a mine underground where they were trying to detect dark matter particles, and then it's kept coming. I mean, efforts have kept on going since, and we have scientists everywhere now looking for the dark matter particle with all kinds of twists and variations.
Yeah. And also, it wasn't always thought that it was a particle. And so originally, scientists were still, astronomers were quite archaic in their instrumentation. And it wasn't until the 70s, 80s, and 90s when we started developing other instrumentation that's out in space, different techniques for observing very faint, non-luminous objects. So one idea, I think it was in the 70s or 80s, was when we started sending out X-ray observatories out into space. We started looking for hot gas in these distant galaxies, thinking that maybe we know that there should be a lot of hot gas in these all galaxies, and perhaps that will account for the missing mass we observe and consider to be dark matter. And it turns out all these galaxies had tons of hot gas that we didn't know about previously, except that wasn't enough mass to account for the 5 times the normal baryonic mass.
Right.
Also, when we say baryonic, we're referring to the 5% of the universe that's composed of normal mass, like me, this table I'm sitting at, stuff like that, or the star, or planet Earth. And then when we say non-baryonic,
palpable matter.
Yeah, non-baryonic is matter that doesn't interact electromagnetically, so it doesn't reflect light, and that's what we consider to be dark matter.
And you said something weird there, because you said that our regular matter is only 5%. And we also said before that there's only 5 times more regular matter. There's 5 times more dark matter than there is regular matter.
25% dark
and so,
matter.
The astute observer or listener might be wondering, what's happening with the rest of the matter?
Yeah, there's 70%.
The rest of that mass is what we call dark energy, which is something we'll get into next week, and that's a whole other thing. But at the moment, for this episode at least, we're only going to look at the 30-some percent of the mass of the universe, which is 1/6 regular matter, 5/6 dark matter. And so we covered the history a little bit, but I think the history would be confusing without us actually talking about the evidence that we have to suggest exactly that to tell us so strongly that dark matter exists and we should be looking for it, and it's not just something that we're wasting our time over. And so, as we talked about, the first piece of real evidence, I think, that kind of backed up the idea of dark matter was this thing of galaxy rotation curves that we talked about. It's this idea that when we look at the solar system, and so relatively small things, Newtonian mechanics, and so gravity, essentially, as we understand it, says that things further out should be going slower than things further in. But we didn't see that with the galaxies, and that led to us seeing these flat rotation curves, and whereby objects near the center were going at exactly the same speed as objects further out. And so to make these flat rotation curves fit with our understanding of how gravity works, one must obviously think there's probably more mass somewhere than we're really seeing. And so that was the first piece of evidence that told us there is dark matter out there. The second pretty major piece of evidence that we have for this dark matter is gravitational lens, is the way that objects gravitationally lens.
Yeah, and so when we talked about black holes the other week, kind of mentioned the fabric of space-time and how it bends and warps if you place an object with high mass. And it's the same thing with large galaxies. And so if we have a galaxy, or a galaxy cluster, and now we have to say that it's 5, in that galaxy cluster, there should be around 5 times the mass in dark matter. then it's a lot of gravity being exerted because I don't know if we mentioned this, but dark matter doesn't interact in terms of electromagnetic spectrum, so we can't observe it with telescopes. It doesn't reflect any light, but it does interact gravitationally, and so we can see how it gravitationally influences light, for example. And so when we when you have something that's very massive, it kind of curves space-time, and so when light from behind it passes around that galaxy, it bends around because of how high of mass it is. And then by studying how that light curves, or how it's what's the terminology again? It's lensed around that giant galaxy. You can study the distribution of mass within that galaxy, and also you can just study the distribution, or what should be the distribution, of dark matter within that galaxy or galaxy cluster that lenses the light.
And so to break it down to slightly simpler terms, lensing is when you have a huge object, and normally, obviously, you wouldn't be able to see what's going on behind the huge object. But the huge object is so big that it bends the space, and it bends the space-time around it. And so it lets us see things that are actually behind it, but that appear to be coming. Well, it lets us see objects that are actually behind this huge thing, but by kind of bending the light around it. So the light is not going straight, it's actually bending around these big objects. And so gravitational lensing, and gravitational lensing allows us to calculate how much mass there is based on how strong the lensing is. And so by looking at gravitational lensing, we've also been able to detect that there is really a lot more mass and a lot more lensing than traditional ordinary matter predicts that there should be.
And then another line of evidence would be the CMB, the cosmic microwave background radiation. And so that was sent or observed. So that's basically the light, I think it's 350,000 or so years after the Big Bang. That was when the universe cooled down to a low enough temperature where basically photons could escape. And that's the...
Yeah, and just to clear that up, at very, very, very hot temperatures, there's some weird things that go on with matter, where the quarks aren't necessarily bound to each other. So essentially what makes up protons and neutrons aren't necessarily stuck together. And there's some weird interactions that happen between the light and the matter, wherein they will collide with each other and create products, and those products will collide with each other to create matter and light again. But that's only at hot enough temperatures. And so the amount of years after the Big Bang that Michael said, 325,000, right?
Yeah, like that.
Is what you said, something like that. Essentially, the universe cooled down enough where those interactions wouldn't happen anymore, and that light and photons aren't necessarily quantumly bound to the matter anymore. So essentially, they're two separate entities instead of colliding with each other to create products, and then those products colliding to create the matter and light.
Yeah, and so when scientists with 3 different satellites, the first one I think being WMAP, then COBE or COBE WMAP, and then most recently in 2013, the Planck satellite that studied the CMB, or the cosmic microwave background radiation. If you look up a map, if you're on your computer or phone listening to this, you can kind of see basically an entire map of the night sky that's either different hues of red or different hues of blue. And those refer to different fluctuations in temperature of the early universe at that point, 350,000 years after the Big Bang. And even though it looks like they're drastically different colors, because one's a deep shade of red and one's a bright blue, they're actually very, very, very small fluctuations in temperature in the early universe. And what scientists have recently been able to do, I think it actually won the Nobel, or half the Nobel Prize in Physics this past year in 2019, is the one scientist made what's known as the power spectrum of that CMB, and he looked at the different area of the different colors, and he said that angular area on the sky versus the temperature fluctuation, he made a map of it, or a graph, and plotted them on both axes, and he got these different bumps that correspond to where the temperature fluctuation is greatest for the given angular size map. And they found that through simulations, once they change the contents of dark matter in the universe, that gives rise to completely different results than what they see in the cosmic microwave background radiation. And so it's very tied to each other in terms of how much dark matter, or the presence of dark matter, and what we observe on that power spectrum. So that's another line of evidence.
Sorry. And so we have basically these three pretty big pieces of observational evidence that tell us that our current understanding of how the universe works is wrong. We have galaxy rotation curves that are too flat, and so that's weird. We have gravitational lensing, which is too strong for what our current mass accounts for, so that's weird. And then thirdly, we have the cosmic microwave background, which behaves in such a way that tells us there probably was actually some other thing, and so like that dark matter, and so that's weird too. So these three pretty large pieces of evidence that tell us our observational evidence is wrong. Our current understanding how the universe works is wrong. Sorry, not the observational evidence is not wrong. And so as we talked about before, that gives you kind of two main options. Either our understanding of gravity is wrong, and so we're not actually seeing missing mass anywhere. It's just that we're incorrectly predicting that there should be more mass. So that's the first option. The second option, obviously, is that there is actually something out there that's physical, it's real, it's palpable, and it interacts gravitationally, and that is dark matter, except that this dark matter is a kind of matter that we have yet to interact with, or we've yet to meet it, and it doesn't interact with light, so we can't see it, and it's just hiding out there. And so there's those are kind of the two main directions that we can be looking at when we're actually trying to think about what dark matter actually could be. And so first of all, I think we should go into what dark matter actually, what the physical
what the theoretical particles are.
Yeah, what these particles are.
So as I mentioned before, not only is there the idea of the particle, but there's also the idea that it could just be a very faint baryonic matter, or matter that isn't explained by something that's dark and elusive and doesn't reflect light. And so I mentioned before the idea of the hot gas that the astronomers observed, but they found that it doesn't account for all of the missing mass in the universe. And another idea that came forward was something known as a MACHO, I believe it's pronounced, which stands for a massive compact halo object. And so that could be a bunch of black holes, or small black holes that aren't not supermassive black holes at the center of galaxies that could account for that missing mass, or a bunch of low temperature, or not low temperature, but very faint dust in the universe, and also a lot of planets, unobserved planets in the universe. And together, scientists believe that could account for the missing mass. But most recently, they've kind of thrown away that idea of it being composed of all these
they've transitioned from very big invisible objects to very small weakly interacting objects.
And I mean, to give credit to the MACHO hypothesis, that is the one that intuitively makes the most sense. Because if someone showed me a picture of a galaxy and said, hey, how much does this thing weigh, I would have no idea. You can't just stick a weighing scale under it, and it's really hard to try to count every single thing in that picture. And
especially if it's really dark.
Especially that if it's really dark. And so naturally one might think we're probably just not seeing it, but it's just regular matter that exists and it's out there. However, increasingly we're confident that we can calculate the mass of these things. And we're confident that we're accounting for everything that's tangible and everything made of baryonic matter. And we still are falling way short of the mass that we should be getting. And so this is really pointing towards the idea that there is probably a physical particle, or there's physical matter out there that we can't see because it's trying not to be seen. It's not just that it's mini stuff that we're not seeing. It's matter that's actively kind of disguising itself. And so there's a couple, and so as we talked about, there's this idea of the WIMP, the massively, the weak weakly interacting massive particle, which
Right.
is just a huge particle that weighs a lot more than the particles that we would consider matter, like the chair I'm sitting on and things like that.
Mhm.
But it doesn't interact with light, and so that's why we're not seeing it. So that's the WIMP option. There's also this other idea of the axion, which is a very, very small particle, I believe, it's very dilute. It exists everywhere within our current matter, and it's so
Right.
small that we can't detect, that it has no impact on the way that our baryonic matter works. However, given how much there is, that could be one of the options for what dark matter is. And many people are looking for the axion dark matter particle candidate, and for that I believe that we're building very, very well. I think there's many ways of trying to detect the axion. A way, which I've heard about, is building very, very sensitive just radios, exactly like the kind that we use to listen to music in our cars. And we could detect some of the signals of the axion interacting with our matter, I believe.
Right, and specifically for radios, as electromagnetism happens to work, radio waves have the least amount of energy compared to gamma rays, and so an axion or a WIMP, something that's weakly interacting with the electromagnetic spectrum and light, would, if at all, if they interact with the spectrum, it would have to be radio waves in a very, very, very small amount. And so that's why we specifically look at radio waves and not something like the X-ray satellites that we sent up previously.
Yeah. And I mean, there's a lot of potential candidates for dark matter. And I don't think, and I mean, some of them, the major ones, such as WIMPs and axions, are kind of the biggest ones, but there's really very little evidence so far that these are actually the answer. And there's loads of other candidate particles that really could turn out to be responsible for dark matter.
And the one issue nowadays is scientists are realizing that they've been spending the past 30 years looking for a particle, whether it be a WIMP, an axion, or something else that we're not sure. And so the question now becomes, is it worth continuing the hunt for dark matter with a particle approach, or could it be something else? Which I think is interesting. And so these I don't know if you call them astronomers or particle physicists, they often do, as I kind of mentioned in the beginning in the news bit when I talked about the mountain underneath, or the mine underneath the mountain in Italy, where they have these dark matter detectors, is they go to very, very quiet places. So the quietest place you can find is likely a few thousand feet underneath a very tall mountain in Italy, or in old mine shafts out west in the continental US. And they have these giant, usually they use xenon and other noble gases in these giant vats that are a few tons to up to 10 tons. And they look for little blips in their detectors as little counts, as particles passing through. And so that's like the nowadays, that's the approach they take in terms of experimental dark matter, looking for a particle. And also, Tom may know more about this, but I know when they started CERN, or the Large Hadron Collider, that was one possibility, is the idea that they could detect the dark matter particle through that in the first few years.
Yeah, with well, just to wrap up the xenon experiments, as why they use big vats. There's predictions that the amount of axions traveling through your body at any given moment is in the millions of trillions of particles. So some insane number. And so,
but it's so small that over a lifetime, only 1 milligram of dark matter would have passed through you.
Right. Yeah. That there's just so many of these particles that are passing through. You figure you would detect at least one within 30 years, just because of the sheer amount that are passing through. But they're so small and so weakly interacting that it is becoming difficult. And so that's why at CERN, they thought they would be able to discover some kind of dark matter. I think specifically at CERN, they thought of the idea to use, so as you may know, normal matter has a counterpart called antimatter. And so they at CERN, they are very easily able to create antiparticles through their collisions in the Large Hadron Collider. And so one theory was that if dark matter is a real particle, then theoretically there should be an anti-dark matter that could be more easily observed than actual dark matter. And so with these high-speed collisions between different particles and the particles that make up atoms and the particles that make up the particles that make up atoms, that they'd be able to detect these very, very, very small and weakly interacting particles when they smash together two objects.
But they didn't.
And then also,
Yeah,
this was a hypothesis in terms of particle dark matter a while ago, but it's kind of been ruled out, and that's the idea of neutrino. So neutrino was often associated with something called hot dark matter, and since then, over the years, once we've been able to learn more about what neutrino is and how much there is in the universe, we've kind of ruled that out in terms of accounting for all the dark matter.
Well, that's what dark matter is good for, because we predicted that a neutrino is dark matter, which was obviously wrong, but we were actually able to discover what a neutrino actually is, and that it's a real particle, and that happens in radioactive decay. And so the particle physics in dark matter may not necessarily be life-changing towards the discovery of exactly what dark matter is, but it gives us a lot of insight into particle physics that we may not necessarily have been looking at in the first place.
And I mean, I even though it appears that the scientific consensus is that dark matter is in the matter form, I have to say I quite like the idea that that our understanding of gravity is wrong, and it's not actually and that I find it I would find that quite cool if dark matter could actually be explained fully by a modification to our understanding of gravity. And there have been many of these different theoretical models proposed over the years. Most of them are insanely complicated because they bring together so many different areas. I mean, not that, because they bring together all of these areas of physics and try to explain kind of how the universe works through all of these different separate areas of physics, and try to wrap it all together into one coherent package that would somehow explain not only how the universe works at the very, very small level, but how it works at the huge level, and how gravity works, and all of this. And
so
go for it.
I was going to say the leading candidate for modified gravity is known as MOND, or modified Newtonian dynamics.
Yep. And so essentially what MOND is it's a model that says that gravity as we understand it works the way that we understand it on the smaller scales, but at the really, really, really big scales, gravity doesn't exactly behave in the same way. And this was proposed as early as the 1970s, except that MOND never successfully explained all of the different observational pieces that we have. So for example, MOND failed at explaining how the dark matter accounts for the way that the cosmic microwave background is. And so for that reason, MOND has been dropped. But MOND was kind of ruled out initially, but since then many scientists have kind of rekindled the idea of MOND.
The main challenge with throwing out the idea of dark matter being a particle and instead having it be a fundamental misunderstanding of gravity is that you would have to test, and this is what happens in all modern physics and astronomy, you would have to test your hypothesis at every single extreme possible, because we very quickly understand what's happening on a scale. If I were to throw my computer against the wall, it's going to hit the wall and fall down, right? But if it was billions and billions of degrees hot, how would that work? Or if it's on a very tiny scale, with particle physics are on a very, very big scale, looking at gravity and galaxies, or if it's extremely cold, like the cosmic microwave background is, how would that behave? And so testing these theories at the very extremes of what the universe is capable of is where we need to be able to have these predictions be right.
Yeah. And I think both ideas, whether it be modified gravity or a dark matter particle candidate, I think both have very big implications, and they both involve a lot of not necessarily new physics, but a lot of like new understanding of how the universe works, which obviously comes along with understanding what something known as dark matter is.
Right.
I know previously from astronomy classes I've taken at university, most professors kind of briefly brush aside the idea of modified Newtonian dynamics, or MOND, just because I think in the astronomy community and perhaps in the physics community, it's kind of been that outlier where not as many people are working on it. So it's kind of ignored. It doesn't pass all the tests, as Joe explained. And they kind of look at it in terms of either being explained by some particle that a detector, like a liquid xenon vet, has yet to detect, just because they're not refined enough. And we just have to wait a decade or two until they're sensitive enough to detect the particle. Or perhaps there's in the next decade or so, we'll come across some other novel idea as to what it could be.
Right. And it's also led to theories that expand outside of our own universe, because it could very well be a mixture between particles and a misunderstanding of physics, but it could also be, I think Michael knows more about this, but that there are parallel universes that are essentially stacked on top of each other, and that the gravity from one universe is able to seep through and affect our universe.
Yeah, and so when we think of the universe, obviously it's uni, so being one verse, that's us. But perhaps as has become quite popular in the past decade or two, the idea of the multiverse, where we're kind of surrounded by a bunch of other universes or universi, and there's a membrane separating these different universes. And gravity is some force that can kind of, this is quite science fiction-y, I believe, and perhaps something we'll never be able to know, because you can't really test something that's not in your own laboratory or in your own universe. But perhaps gravity is some force that is able to seep through the membrane separating the different universe. And so when we see dark matter in our galaxy, perhaps we're seeing it just seep through from a galaxy in the nearby universe. That's obviously far out there and more of like a thought experiment, I'd say. But yes.
Right. And, that's something that we'll never be able to prove or understand, but, it's still a possibility if we never actually end up finding anything.
That's true. And also, as we mentioned before, we see dark matter now, and because we talked about the 3 lines of evidence for dark matter, being the rotational curves, gravitational lensing, and
the CMB,
the cosmic microwave background radiation.
Right.
But one thing we also didn't mention is that dark matter has a lot of implications when we're studying the evolution of the universe. And so dark matter, it turns out, we think it's very clumpy, meaning that it's very attractive to itself. And so with a universe without dark matter, we don't see the large-scale structure, or when we run simulations without dark matter, we don't see the large-scale structure in the universe as we see today. And so a common way to describe it is the cosmic web, or these filaments of dark matter that run to and fro in every which direction. And along these galaxies kind of gravitate towards and kind of stream through like a highway, where you have one lane going one way and the other lane going the other way.
Right.
And without the exact percentage of dark matter as a ratio to the normal amount of matter and dark energy, we don't see in the simulations the structure we observe today. And so it's something very fundamental, whether it be modified Newtonian dynamics or whether it be a particle. We know, as we've mentioned, that it's there and that it's necessary to explain what we observe today.
Right, and we'll cover more of the evolution of the universe in part 2 in next week's episode when we talk about dark energy. But the evolution is very interesting when you think about it, especially with that matter web that you're talking about. It draws a lot of parallels to like a circulatory system where the main sources of everything run in or along all the veins and arteries that go in your body.
Like the neurons of a brain.
Exactly, yeah. And so having those connections could, we can show, a picture of the cosmic microwave background. If you happen to look it up, all the different fluctuations could be caused because of that dark matter web that everything happened to clump around. Because, if dark matter has spread across the universe, then regular matter is going to be gravitationally bound. And, that's how, galaxies were first created and stuff.
Yeah. And I think it's dark matter in general is just a very interesting subject because I don't know, maybe I'm missing something, but I don't know if there's been an unknown in the realm of astronomy and physics for this long.
Right.
Yeah.
Of course, like there have been things we haven't known, but we just didn't realize we didn't know them. But in terms of trying to observe something and try to explain the fundamentals of what something is, it's been quite a while. Being now 2020, and this being first introduced in 1933 by Fritz Zwicky.
And the funny thing is that it seems to be a subject that we can just sidestep.
It's true.
It seems not to, we in the pursuit of our understanding of everyday and of regular physics, it seems to be completely unimportant that we're not understanding what 95% of the universe is exactly. And that's very bizarre to think that we can just keep going and try and keep understanding things better and better without actually kind of addressing the elephant in the room.
Right.
And so it's interesting you say that, Joe, just because my research professor who studies galaxies, one interesting thing is dark matter is very, very important to how he understands how galaxies interact with each other and the evolution. And there's something called the dark matter halo that extends very, very far out beyond what we observe of the stars in a galaxy. And he's told me multiple times he doesn't care at all what dark matter is, whether it's a modification of gravity or whether it's a particle or something we have never even thought of. Like, all that matters is that he can somehow in a simulation or in his observations account for that 5 times the normal matter, or approximately.
And that'll give you the correct models. Like, you don't need to understand what it is.
You don't have to understand what it is, which I think is really, really wacky.
I also think the most challenging part is, it's like Joe mentioned, even though dark matter is 5 times normal matter, at about 25-ish% of the entire universe, it's so entangled with all the other unknowns that we don't know about the universe. Like, dark matter and dark energy, I guarantee, are hand in hand with one another, and without understanding one, you can't understand the other. And so we're at a big barricade of understanding the universe.
But also, I think a common misconception is people kind of confuse dark matter with dark energy just because they both start with the same word, dark.
Right. I mean, they're separate. They're just so entangled with one another.
We don't even know, exactly what they are. I don't know if they're tangled with each other, other than like they're the leading unknowns in the scientific community. And discovering them would be, I don't even know what they are.
Yeah, but like
paradigm shifting.
It's like one affects the other, and you can't fully understand one without the other.
Yeah.
And also a side note is something we didn't bring up, but dark matter isn't distributed evenly. I mentioned the cosmic web, so it falls along these filaments. But I believe in some galaxies there has been very, very, very little amounts of dark matter observed, and so that's
it's missing.
That's another question that's come up in the past decade. Is not only do we understand that there's this dark matter in the universe, but why does it show up in some galaxies more than it does in others?
We know there's missing matter, but in some places there's missing matter.
Yes, so it complicates things.
Right. And I know that some new theories are coming out where dark matter. It's like I mentioned the other week in a previous episode of Not So Sirius, how scientists have confirmed that there's a 4th spatial dimension, and so maybe dark matter is purely a 4D particle, similarly to how the anion that we mentioned today is a 2D particle, and that's why we can't fully understand it.
Yeah. But suffice to say, it's going to be very interesting to find out what the explanation is for dark matter, if we ever find one. We might never.
Right.
Hey everyone, thank you for listening to this podcast episode. This is Michael.
This is Sam.
This is Tommy.
And this is Joe.
If you're listening to this on YouTube, make sure to like, subscribe, and share with your friends. And if you're listening on Apple Podcasts or Spotify, make sure to leave a review. All of the show notes can be found either in the description below or on our website. Thank you again for listening, and we'll see you next week with more Everything Astronomy.